Thank you. Thanks. Well, thank you very much. I would first like to make a formal thank you to the University of Costa Rica and to the Structural Engineers Association of Costa Rica for the opportunity to come here and talk to you about displacement-based seismic design of structures. And what we hope to do in this is to introduce you to this new technique, which I hope will make you think about the way in which we design structures for earthquakes, and to realize that the way in which we do it at the moment is not logical and can result in unsafe structures, and that we really need to start thinking in a completely new way about how we should design structures. So the title, of course, we have here. And essentially what we're going to be discussing is that within a performance-based environment, what should be the structural strength, the base shear strength, if you like, of a building, how this should be distributed through the structure in a way that is different from what we do at the moment, but which creates the best seismic performance. How can design be elevated above analysis? Because there has been a trend in the last 30 or 40 years with the advent of such powerful computers as we use at the moment for the design to be governed by analysis, which is completely the wrong way around. Analysis should be being used to verify designs which come from a logical interpretation and from the experience of the designer, and not to be dictated by analysis, which, as we will show, generally cannot be done adequately at the start of a design because we do not have sufficient information. And also, we need to discuss how should the strength of capacity protected actions be done. In other words, we will talk quite a bit about recent developments in capacity design. This is ensuring that you don't get plastic hinges forming where they should not form, and ensuring that undesirable inelastic modes of deformation, such as shear failure, should not occur. And the basis for this is a book which has recently been written, in which Michele and myself are the principal authors, but I would also like to acknowledge the contribution of our co-author, Professor Kowalski from the University of North Carolina, who really should be the one who should be here because he speaks Spanish, and then we wouldn't have to have the translations. Anyway, this book is a fairly major book. To my mind, it's the most important book that I have been involved with because of the way in which it is describing a complete new process for seismic design. This first session is introductory. I'd like to give a brief overview of the book itself, what the chapters are, because we will not have time in the presentation to discuss the entire book, but also I want to spend this session to discuss what's wrong with the way in which we do seismic design at the moment, to look at some of the assumptions that we make and to try and persuade you that these assumptions are invalid and can result in very great inaccuracies in our design. So the book itself is a culmination of more or less 15-year research effort into the development of a new rationally based, but particularly a simple seismic design procedure. And by simple, I mean it's more or less equivalent to the old equivalent lateral force degree approach that we used in force-based design. A single degree of freedom system, but not one that we lose any accuracy because of the fact that we describe the response by the fundamental inelastic mode of response. It's performance driven. In other words, we describe the performance in terms of limit state strains or limit state drifts and design the structure to achieve those particular limits, which might be serviceability limit state, damage control, failure, whatever you like. It covers a wide range of structural types, as you'll see shortly, and a wide range of structural materials: concrete, steel, masonry, timber, precast. It includes a complete re-evaluation of capacity design. Many of you will be aware that this procedure of capacity design originated in New Zealand, but the basis for it really hasn't been examined for the last 30 years, so we have done some re-examination. There are a large number of design examples. You see 39 of them completely. Obviously, we don't have time to go through so many. And it's intended primarily as a document for design engineers. It's not so much a research text, though we believe that the information in it will be valuable and interesting to researchers and graduate students. I'll briefly go through each chapter, just showing what it has in it in a very brief sense. Chapter 1 is an introduction, which is what I'll be talking about later in this session, which discusses the problems with force-based design and establishes why it's necessary to change from current force-based design processes. And one thing that we'll look at in a great deal of detail is simple structures such as this bridge under longitudinal seismic response with different height piers. And we'll look at the current approach where we would calculate what the stiffness, what the period, don't know why that went back, and how we would distribute those forces. And we'll show that the way in which that is done is completely illogical in terms of getting a good seismic performance of a structure that is intended to respond inelastically. Chapter 2, which is really going to be discussed in the second session, is looking at the seismic import for displacement-based design. And we don't use acceleration spectra, we use displacement spectra such as these. They tend to be very simple in form, but we will show that we can develop these directly from source mechanisms rather than necessarily the way that we have them in codes. And this just shows different spectra for different magnitudes of earthquakes at 10 kilometer difference. And you can see that there's a very great deal of difference in terms of the displacement spectra for a magnitude 6 and a magnitude 7.5. We also will be looking at the influence of viscous damping on this, because we will find that we describe the structural performance in terms of equivalent viscous damping rather than just ductility. And we have differences between the displacement spectra for what we might call normal conditions and other ones where we might get forward directivity and velocity pulse conditions govern. Chapter 3, which will also be dealt with in the session, looks at the fundamentals of the procedure itself, and it sets the mathematical and logical background for direct displacement-based design and discusses philosophical differences between the force-based and the displacement-based approaches. And there's a lot of additional information about various things such as P-delta effects, how we combine gravity and seismic loads, and I'll hope to persuade you that we don't need to combine them. We can design for them independently. And various other aspects such as torsion and capacity design in principles. It also includes this particular diagram, which is the most important one that we will be presenting in this session, not in this session, in this seminar, and which you will see very many times, which essentially the description is that we have a structure which may be a building, a bridge, a wharf, anything, which we describe by a single inelastic mode of response, and we describe the force displacement response not by the initial stiffness, but by a secant stiffness to the maximum design displacement. We have relationships between ductility and damping for different structural systems, and we have a displacement spectra set for different levels of damping. And we'll come back to this many times, so I don't want to waste time with it just now. Chapter 4, which we'll discuss a little bit at the very end of the seminar, deals with analysis tools for direct displacement-based design. And one of the things I should emphasize is that the book, for those of you who are buying this, also comes with a CD at the back which has a number of computer codes on it for different types of analysis. There's a program called CUMBIA, which does moment curvature analysis, and two dynamic inelastic time history analysis programs, ROMOCO and SEISMIC. So these are quite valuable to the design engineers because they enable you to do quite complex structural verifications if you need to. We'll look particularly in this at equilibrium considerations and tend to use equilibrium rather than stiffness-based structural analysis to determine the distribution of forces, because we'll show that in fact there's not much point in doing a stiffness-based analysis at the start of a design when you don't know what the stiffness of the members are, and anyway it distributes the forces through the structure incorrectly if you are basing it on an elastic analysis and the structure is responding inelastically. Also information on shear strength and capacity design and so forth. Chapter 5 is a detailed chapter on the particular aspects of frame buildings that might be of interest to the designer, and we'll talk about that in the first session tomorrow morning. And one of the things that we will look at also is looking at structures which might respond elastically to the design level earthquake, and we'll show that from a displacement-based point of view, particularly in regions of moderate seismicity, many structures can be shown to respond elastically to the design earthquake no matter what strength you put into them. And this can simplify design. And this diagram just compares yield displacement shown by dotted lines of structures of frame structures of various heights with the designed maximum displacement for earthquakes of different peak ground accelerations generated by different moment magnitude earthquakes. Chapter 6, Structural Wall Buildings, again discusses issues that are relevant to wall buildings, including these aspects here. We'll go through that in the second session tomorrow morning, particularly torsional response, capacity design effects, foundation rotation, and so forth will be dealt with in this. And also a little time will be spent with coupled wall design, and this is particularly an aspect of structures which cannot be dealt with adequately by elastic analysis. The results that you will get from elastic analysis of a coupled wall structures have no bearing on what is going to happen to the structure when it's subjected to the design level earthquake. Whereas by displacement-based design, we can come up with a very logical structural system and that performs very well. Part of the aspect is re-looking at capacity design equations, here shown for moment capacity and shear force, and we'll show that in order to protect against shear failure in structural walls, we have to be a little bit more careful than we have been in the past. We also deal with dual wall frame buildings. We'll spend a little time on this. The behavior is very similar to that of coupled wall buildings, and pretty much the same aspects are considered. The most important thing in both of these cases is that the designer at the start of the process makes a conscious decision what percentage of the lateral force is going to be carried by, in this case, the walls and what percentage taken by frames. And it's not something that you can get logically from a structural analysis, but there is no reason why you should do anything other than to make your own decision about this based on experience. Masonry buildings, this chapter deals essentially with unreinforced or very lightly reinforced buildings, such as extensively used in Europe and Central and South America. And it's shown that displacement-based design is a much more rational way of designing such structures than force-based considerations. And the coupling between walls by floor slabs and spandrels is rationally considered with an innovative design approach, which again is very simple, but not based on stress considerations or force considerations. Just the sort of structures that we might be dealing with shown here. Typically, this is really a matter of seismic assessment because the structure will be almost entirely governed by architectural considerations, and it's a matter of determining whether the structure requires some modification to perform well. Timber structures, a brief chapter discusses the design of timber structures and pointing out that really force-based design is completely inappropriate because of the hysteretic characteristics, whereas displacement-based design is very simple for such structures. And we show different types of structural systems that might be of interest. We'll come back very briefly to this in a final session. Then today's session is primarily on bridges, though we will be in the introductory sessions, that's in the morning, talking about buildings as well as bridges. But there's a major chapter on the use of displacement-based seismic design for bridges, looking at longitudinal versus transverse design, elastically responding bridges, influence of bearings and foundation flexibility and the damping associated with these, how we incorporate those into displacement-based design, which is simple and rational but can't be considered in a force-based environment correctly, P-delta effects, which are very important for bridges, different foundation conditions, and capacity design. And one of the aspects that we have to look at the start is the expected displaced shape, the characteristic mode shapes of the inelastic first mode of deformation. And we'll come back to this later on in the day, where we see different support conditions and different relationships between the flexibility of the superstructure and the piers results in different inelastic displacement shapes. So chapter 11 deals with structures with seismic isolation and added damping, and essentially, though it hasn't been recognized, at least even in the United States, displacement-based seismic design has been used for the design of such systems for some years because it's impossible to design a structure which has an initial stiffness which is governed by structural elements and perhaps seismic fuses and then has seismic isolation. It's impossible to design that by force-based considerations. So Michele will be spending some time on this in the afternoon sessions tomorrow. And just some idea of the different types of structures that might be considered in this, which we'll look at in more detail later. There's a chapter on wharves and piers, again, because these structures, particularly when you have a marginal wharf which has piles of different heights, it's very difficult to get a rational design of this by force-based design, but displacement-based design works very well for them. So not something we'll deal with in this, but it has been considered of sufficient importance so that the Port of Los Angeles has adopted displacement-based seismic design code, which I've helped them develop over recent years. There's a chapter on displacement-based seismic assessment. It's a procedure that can be used efficiently for assessing existing structures as well as for design of new structures, though we will be concentrating primarily on new design. And we'll look at different examples associated with seismic assessment. And then finally, the last chapter is a draft displacement-based code for seismic design of buildings. Just a very simple document to show what sort of code clauses might be used to incorporate this into design codes, and it's intended as a starting point for the development of seismic codes. We'll talk again a little bit about this more later on at the very final session, where we talk about how can we get this going as a design procedure. Right, let's start on looking at what's wrong with the way in which we design structures for earthquakes at the moment. And first, just a very little bit of background information. Current seismic design philosophy generally is developing towards a multi-performance level consideration, in that under the serviceability level earthquake, which will be designed by probabilistic characteristics, there should be no damage requiring repair. For the design level earthquake, repairable damage, and under some extreme earthquakes, there should be no collapse. To my mind, designing for 3 different levels is a little inefficient, and generally it will be sufficient to perhaps just design for the design level earthquake and maybe do some checks for the others. But in particular, it's becoming common in the United States to design, or to be required to design, for an extreme near collapse level of earthquakes, and FEMA is requiring that. I don't really like this because I think it's very difficult to define that near collapse state with much accuracy for structures, whereas the repairable damage state we can. Just some examples. Here you can see the Kobe earthquake 1995. This particular bridge pier, a modern bridge pier, it has survived but is not in very good condition, but the structure exceeded the design intensity by more than 50%, and so we could call this an extreme event, and that therefore this structure has performed satisfactorily, though clearly it's undesirable. Whereas this, designed a little earlier, clearly under the same earthquake, is unacceptable. But I don't, as I said, like either of these particular ones. We could have designed this so that under the extreme earthquake it performed much better, and this one also could have been designed better. But let's start looking at the problems with force-based design. If we make some initial thoughts about it, structural damage, which is related to performance level, either no damage, repairable damage, near collapse, structural damage is strain related. It depends on the strains in the material, not the forces or anything of that sort of nature. For example, if we take reinforced concrete, we know that the cover concrete in a plastic hinge region will start to spall at a strain of about 0.004. We have equations which give us safe limit straits for repairable damage of concrete. We know that if the maximum strain in reinforcing steel in an earthquake exceeds about 1.5%, then we're likely to end up with residual crack widths that require repair. So in each case, these are strain-related aspects, and we can define a performance level for structure in terms of strains. Non-structural damage, particularly in buildings, is generally related to drift. That's the displacement of one story relative to the story below, perhaps. And such things as mechanical connections, partitions, non-structural aspects in a building tend to get damaged when the drift exceeds a certain level. Now, both the structural aspects, the strain, and the non-structural aspects, the drift, can clearly be integrated to get displacement of the structure if we know some idea of how that's distributed. So therefore, performance levels can be directly related to displacement. Whereas if you try to make a relationship between performance level and strength or forces, you cannot do it. There is no such relationship, and I'll show later on in this lecture that force or strength is a very poor indicator of the damage potential of a structure. We'll come back to that. If we look at design to elastic acceleration spectra, which is the current way in which we do design, which I call force-based design, the assumptions are that elastic force levels, which are dependent on initial stiffness, are of prime importance. We say that the elastic stiffness is known at the start of the design. We don't. The elastic forces we assume can be reduced by performance factors such as behavior factors or force reduction factors related to the ductility capacity, which are dependent on material and structural type. So we assume that for a given structural type, there is a particular force reduction factor or behavior factor that we would use that is unique for that structure, regardless of its geometry. We can show very simply that that's invalid. We assume that the maximum transient response is the issue rather than residual displacements, and that is not necessarily the case. We assume that the maximum displacements of an inelastically responding structure are well estimated by the elastic response values dependent on the initial elastic period, which we don't know. And this is also invalid. We assume that safety is increased as the strength is increased. And this may be almost true, but it is such a tenuous relationship between strength and safety that it is not worthwhile considering. Now, right at the start, I'd like to point out that displacement-based design is not a difficult aspect. It's very simple. And in this slide here, we compare the equivalence of force and displacement-based design for a structure that we might be designing for elastic response. Forget about ductility for the moment. Just consider elastic response. And we'll assume that we have a structure where we know what the period, the fundamental period is, 1 second in this case. And we could have on the left-hand side here, we have an acceleration spectra. On the right-hand side here, we have an exactly equivalent displacement spectrum. So we can generate one of these from the other, but they are exactly equivalent. So we look at how we might design in force-based design. Well, what we would do is we would say from the period here, we could calculate the acceleration response, which is the acceleration AT here, and the force, the design force then would just be the mass times this acceleration, which is perhaps in dimensionless terms, times the acceleration g of gravity. Okay, so we've calculated what the strength is, but we also want to know what the displacement is. Well, we calculate the displacement as the, I'm having trouble with this mouse, as this force divided by the structural stiffness. And now we have the two things we need, the required strength and the response displacement. Well, if we wanted to do this from a displacement point of view, instead of using the acceleration spectrum, we would use the displacement spectrum. We would again enter with the known period, and directly from the displacement spectrum, it would tell us what the displacement response is. So we've got that piece of information immediately. And to calculate the required strength, we would just multiply that by the stiffness, K, and that would tell us the force. And of course, the force and the displacement would be the same regardless of which procedure you used. Looking at that again, then we would say that we're required to know both the strength and the displacement for design. Force-based, the procedure is what we have shown there, and you can see there are 5 steps to do this. First, we calculate the stiffness. From the stiffness, we calculate the period. From the period in the acceleration response spectrum, we calculate the acceleration. From that, we get the strength, and from the strength, we get the displacement. For the displacement-based approach itself, the procedure only requires 4 steps. We calculate the stiffness, the period, we read off the displacement, we multiply by the stiffness, and that's the force. So it's actually a little bit simpler than using the force-based design, but there's nothing magical or nothing complex about using a displacement spectrum rather than an acceleration spectrum. Structural modal analysis, I hope to persuade you that the way in which we do this doesn't make any sense. So we're very familiar with it and the way in which we combine modes. And we think that because of the fact that we are using a larger number of modes than we would use for an equivalent lateral force procedure, that we are getting a better approach for the design of a structure in terms of considering the higher modes themselves. Typically what we will do is calculate the participation of each mode, calculate, for example, the base shear associated with each mode, and then we'll combine them together according to either a CQC or a square root sum of the squares approach to find out what the base shear would be, and then we would divide that by the force reduction factor that is appropriate for that structure. Now, in doing that, it's completely wrong because the inelastic response is only related to the first mode, and we should not be reducing the magnitudes of the higher modes by that force reduction factor. So by the procedure we use at the moment, we are not considering the higher modes adequately. And we'll show you that in relation to wall structures tomorrow in the second session of the morning. So problems with force-based design as we see it. First, in design, we assume that the stiffness of a material, of a structure, let's say the architectural design comes on, we size the particular structures, the elements, and then we say, right, we know what the dimensions of the particular members are, therefore we know what their stiffness is. Wrong. We don't know what the stiffness is until we know what the strength is. Period calculation is based on inaccurate estimates of the stiffness, because we don't know what the stiffness is at the start of the structure, of the analysis, or we use height-based equations which are ridiculous and out by at least a factor of 2 for determining what the period is. Ductility, capacity, and force reduction factors, as I've said, these aspects have some problems which we'll look at. Ductility of structural systems are not unique for the structural system, but depend on the way in which the geometry of that system is there. We'll look at some of these aspects here. Structures of dual load paths will show, particularly for bridges, is a problem. And the relationship between elastic and inelastic displacement demand, typically we use approximations such as the equal displacement approximation, or we use the equal energy approximation depending on what part of the world we're in, and we show that we really don't know what to use for that. And if we don't know, and if we at the same time recognize that displacement is the most important part of the structural response because it's related to damage, then it's pretty bad what we're doing in our design. Let's look at force-based design and the interdependency of strength and stiffness. Typically in the design, the member sizes are assumed at the start of the design process. We always have to do that no matter what procedure we use. Then the member stiffnesses are assumed. In some codes, we use the gross or uncracked stiffness if we're talking about reinforced concrete or reinforced masonry. In others, perhaps we use 50% of the gross section, or maybe we have a more sophisticated code which provides some variation depending on what type of structural element, like a beam might have 35% of the uncracked stiffness, or a column might have 70%. But there are still assumptions which are independent of the strength. The periods are based on these assumed stiffnesses, and you can see that in a typical case, if we compare the difference between an assumption of 35% I gross and uncracked section properties, the design forces can vary by 40% at least, which is a pretty coarse approximation. And then one of the things which is particularly bad is that we distribute the forces through the structure to members in proportion to this assumed stiffness, which is invalid. Well, is it really invalid? Here's an example which relates to a bridge pier of a particular size. The diameter is 2 meters, the concrete strength 35 megapascals, the yield strength of the reinforcement 450 megapascals, and this has been analyzed. These are moment curvature results in the initial stage of response for this particular section where we vary the axial load ratio, which is shown here. The axial load is varying between 0 and a ratio of 0.4, and also the reinforcement ratio between this one is 1% reinforcement and this one has 3% reinforcement. Now, we can make bilinear approximations to the response, which give us some idea of what the stiffness is. So don't look at the solid lines, but look more or less at these dashed lines, which represent a bilinear approximation to the behavior. The slope of that, in terms of moment curvature, is the elastic stiffness EI. That's the effective stiffness of the element. So you can see that the stiffness is varying quite dramatically in any one of these graphs. But as we go from this graph to this one, it varies even more. So the stiffness is a variable, but perhaps one of the interesting things is that the corner point, the yield curvature shown by the red dots here, that is almost constant between here and here. So if we look at that in more detail, what we see on the left-hand side is the dimensionless nominal moment of the section. That's the moment that we might use for design. And we see that as we change the axial load ratio, or as we change the, this is on the left-hand side, the axial load ratio, or change the reinforcement ratio, the flexural reinforcement ratio, we change the moment capacity greatly. In fact, it could vary anywhere between this value of 0.02 up to 0.18. So about 9 times variation in the moment capacity going from one to the other. Whereas if we look at this side here, what we see is that the yield curvature in all of these cases varies by less than 10% of a constant value. So in force-based design, well, what this looks at then, if we combine these things, in terms of the stiffness, if we divide the appropriate nominal moment by the yield curvature, which will give us the stiffness, and we express that as a ratio of the uncracked stiffness for this same section, the dimensions have not changed, the stiffness ratio can vary between 12% of the uncracked stiffness up to 90% of the uncracked stiffness. And in design, we assume that there is no variation. We assume that it's a constant value. Now, what's the point in doing a very sophisticated computer analysis to govern the design when you use a stiffness value which can be out by a factor of 2 or so? There is no point, and you're not doing the right sort of thing. We need to have an analysis procedure which is not dependent on the initial stiffness. Either that or we have to do an iterative process. So we do a design where we assume what the stiffness is, calculate it, distribute the strength through, recalculate what the stiffness, do another analysis until we get to stability. And if you're going to do that as a design engineer, you're going to lose a lot of money because you're going to spend too much time. If we look at, well, what I would like to just emphasize again on that basis is that the stiffness is not a constant value, but the yield curvature for a particular section is independent of strength within a very small margin. We'll come back to that again. If we look at another element, such as a characteristic beam column element of a frame, which represents the part of a building frame from mid-column height in one story to mid-column height of the story above, and from mid-bay, mid-beam length on one side to mid-beam length on the other side, the sort of thing that has been tested hundreds and hundreds of times in various laboratories through the world, then what we could do is to look at the yield drifts of these elements and make some estimates as to what these might be. And we can show that, of course, the drift, the yield drift, that's the angular rotation at yield, will depend on flexibility of the beam in flexure, flexibility of the column in flexure and in shear, and flexibility of the joint itself. So quite a complex aspect itself. So we say that the elastic deformation contributions to the drift of a beam column subassembly include beam flexure and beam deformation, column flexure and shear deformation, and joint shear deformation. But if we look at the magnitudes of these and make some approximations, we find that in a design where we use the weak beam, strong column approach, that is, we expect the plastic hinges to form in the beams, not in the columns itself, then the most important thing is the flexibility of the beam. And we come up with this very complex relationship for estimating the yield drift, shown by this yellow expression here, which says that we can approximate the yield drift by 0.5 times the yield strain of the flexural reinforcement in the beam times the beam aspect ratio. That's the length of the beam between column center lines divided by the beam depth. Now, there's a lot of things that should be incorporated in this that we haven't included. For example, if we compare this against experimental data, where we've taken a data set of about 45 beam column joints, and variables include the column height to the beam length aspect ratio, which is not included in that expression, the concrete compression strength, not included in that expression, beam reinforcement yield strength, that is included because that's the EY, the yield strain there. Maximum beam reinforcement, not included in that expression. Column axial load ratio, not included in that expression. Beam aspect ratio, yes, that's the other thing. So a lot of things are not incorporated in there, but when we look at how that fits the data, that simple expression, you see it's pretty good. Here's the theoretical drift ratio on the bottom versus the experimental drift ratio on the upper line there. These are the experimental data from test results from the United States, from New Zealand, and from Japan in particular. There's only two data points that don't seem to fit very well, and these are these two ones up here at the top, which are from American data, and those are ones where the beam reinforcement slipped through the joint even before yield. So the actual standard deviation, or the coefficient of variation, is about 13% from that, and the average is very close. So what use is this? Well, in force-based design, absolutely nothing. It's no use to you to know what the yield drift is. But in displacement-based design, as we will show, this is a critical piece of information. Because if we know what the yield drift is, and we can determine what the limit state drift is for the structure, then we know immediately what the ductility demand on that structure is. And we will know this before we have any idea of the strength. So we'll know the ductility demand of the structure for a performance level before we have any idea of what the strength is. And that is extremely useful to us later on in this procedure. It's also worthwhile saying, to look at steel structures, because people say, well, concrete is a difficult material. If we're doing a steel design, of course we know what the stiffness is. It's elastic. There's no problems with it. But of course that's completely wrong, because you don't know. When you put in your steel design, you typically are deciding on a depth of the steel members, say the beams itself, but you have an alternative, a variety of possible flange thicknesses that you will choose. You'll choose, once you know what the required strength is, you'll choose the flange stiffness for that particular class of wide-fanged beam or whatever it is that you're using, and determine the strength. But in doing that, of course, you change the stiffness as well. If you change the strength, if you change the thickness of the flange, you change the strength and you change the stiffness in direct proportion to it. So you start off with an assumption of the stiffness, you put in the strength, changes the stiffness. You do another analysis with a new stiffness, it changes the required demand because the period changes, you need new stiffness, you need new strength, and so forth, and it goes through. But you don't, in a steel structure, have any more idea of what the stiffness is than you do in a concrete structure. The point of this is to bring to the emphasis the fact that we don't know what the stiffness of a structure is at the start of the design procedure, and therefore doing a structural analysis of great sophistication, multimodal analysis based on the stiffness doesn't make much sense. But by doing the sorts of analyses that I've briefly described, we can come up with some information on the yield curvatures of different types of structural sections, such as circular columns, rectangular columns, cantilever walls, T-section beams, and so forth, where they're all of the same form. It's some number times the yield strain of the flexural reinforcement divided by the overall section depth. D for the diameter of a column, H for the depth of a column itself, of a rectangular column, and so forth. Also, for concrete columns, we have an expression for the yield drift, as we've already pointed out, but we can do the same thing for a steel frame. We can determine what the yield drift is independent of the strength. So all of these aspects are independent of the strength, meaning that we can get to an estimate of the yield displacement of a structure without knowing what its strength is at the start of the design process. And this is important for displacement-based design, whereas for force-based design, we cannot come up with an accurate estimate of the stiffness at the start of the design process. So, summarizing that, what does it mean in terms of the way in which we currently do our design and what we should be doing? The left-hand side represents the assumption that we make in force-based design in relation to the moment curvature response. And there are shown here 3 different moment curvature responses for 3 different levels of strength. You know, the same section, but we perhaps change the strength excuse me, by changing the amount of reinforcement or the amount of axial load, whatever it is. And the assumption in force-based design is that the stiffness is the same in each case, and therefore the yield curvature is different. And we also assume that by this approach, by changing the required strength, we can make all elements of an inelastic system yield at the same time. It's impossible to do. But notice that what we're saying is that the yield curvature varies and the stiffness is constant. The real situation, as we change the strength, is that the yield curvature stays constant, and since the strength increases, the stiffness changes. So stiffness and strength are directly proportional to each other. They're interrelated in a way that is not recognized in our current design. Now let's look at another problem with force-based design, and that's the assumptions of system ductility. We assume that for a particular structural system and material that there is a unique ductility capacity for that class of structure, a frame structure or a wall structure, and hence a unique force reduction or behavior factor. For example, it might be that the value used for design is a force reduction factor of 6, so this will depend on the country. And for wall buildings, maybe it's 4, and for concrete bridges, maybe it's 3. But again, this will depend on which country you're in. For example, this is shown here where I emphasize the difference between concrete structural walls in terms of different countries. So on the US West Coast, a value of 5 is generally considered appropriate. In Japan, somewhere between 2 and 3. New Zealand, up to 7.5, which I'm very much ashamed of because it should not be anything like that high. And in Europe, typically about 4.4. So what does it tell you? It tells us that we don't know what the right relationship is between the force reduction factor and the structural class. And that's true, we don't. And different code committees have waved their arms and come up with a particular number and put it in there. But if you see that sort of variation, what you see is that it's not something or other, or what you learn, you think, there must be something wrong with this. There must be something wrong with the way in which we characterize the ductility capacity. And the reason is that the ductility capacity is not a constant for a particular structural class, but it depends on the geometry. And this is the simplest way, and you can look at this, because there is no simpler structure than a simple single degree of freedom bridge pier. And if we look at 2 examples, the exact same column with the exact same reinforcement in it, the same diameter, the same axial load, and the same amount of transverse reinforcement confining it, we can do calculations to determine what the yield displacement and what the plastic displacement is for these structures, and therefore determine what the ductility capacity is. And what we find is that for this squat structure here, very squat itself, the ductility capacity is 9.4, but when we stretch that column up to almost 3 times that same height, the ductility capacity drops to 5. So we get almost a factor of 2 difference in the ductility capacity of this simple structural system. And so what would you use for a bridge pier? What is the correct value to use for the ductility capacity? And the answer is there is no such number. So codes which specify the behavior factor or the force reduction factor for a class of structure are going to end up with structures with different degrees of safety against damage in an earthquake, which is not a very good thing to do. Now look at this thing. We mentioned or showed this slide a little bit before in terms of simple structural response. And this bridge here, we consider just longitudinal response. It looks like it's locked in at the abutments, but that's not the intention. It's meant to be free at the abutments to move longitudinally. And we have 3 columns of different heights. And we have here the elastic response spectrum and the ductile response spectrum, which is found perhaps by dividing this by a factor of 3, whatever it is. What's the design process? This is a very simple structure. It's a single degree of freedom system, if we assume that the mass of the piers is not very significant. So we would calculate the longitudinal stiffness of the structure by adding the stiffnesses of the 3 piers. So let's assume that they're fixed at bottom and also at the top, and that the superstructure is rigid in comparison with the piers, which is a good approximation. So we would say that the total structural system is just the sum over the 3 stiffnesses of 12 EI over h cubed. All right, we can then calculate the period. Of course, we don't really know what I is, I've already mentioned that, but we calculate the period, and then we calculate the base shear as being the elastic response for that period times the mass divided by the force reduction factor, which, as I've said, we don't know what it should be. Then we would distribute the force to the piers in proportion to their stiffness. And we do that on the assumption that we can force those 3 piers to yield at the same level of seismic force, which is ridiculous. We then calculate the displacement, perhaps from the acceleration response, multiplying the acceleration response by t squared over 4 pi squared, the normal way of converting from acceleration to displacement. All right, well, let's look at the problems associated with that. We've said the stiffness, the period, and the way in which the force is distributed. Well, the first question is, what value should we use for EI? And we said, well, the value for EI depends obviously on the strength of the elements. We've shown that it's not a constant value. When the system cracks, it's going to vary. What value for ductility should we use? We've shown that the codes put in a value which depend only on the structural type, but we've said that, well, this column C will have a high ductility capacity, whereas column B, which is tall, will have a lower one. But what's more, what is going to be the ductility demand on these? The displacement will be the same, but the yield displacement will be different. The first thing we say is that force-based design with the column stiffness, let's look at what we were doing in the force-based design. The column stiffness, depending on what the degree of fixity at the top and the bottom is, there'll be some constant here. I've mentioned 1 over 12 before, times the stiffness of the element divided by the height cubed. So initially in force-based design, we would assume the same stiffness in terms of section stiffness EI for each of the 3 columns. Then we would distribute that force to the particular columns in proportion to their stiffness, and that would mean that the shear force carried by those columns would be in proportional to h cubed, inverse of h cubed. The moments at the base of each of those columns would be found from the force times the height of the column, so it would be inversely proportional to the square of the height. So a force-based design will say this short column here is going to have a very much higher moment demand than this tall column here. All right, so if that happens, then what we need to do in force-based design, recognizing that the moment here is perhaps going to be 4 times as high as the column here if the height ratio is 2, is we'll put something like 4 times as much flexural reinforcement in this column as we would in this column here. Now, if we put more reinforcement into this column, we've shown that that increases its stiffness. So because we're rational engineers, we say, okay, we'll do a second iteration. We'll do a second iteration where we increase the stiffness of column C relative to that of column B and do a reanalysis. And what that tells us is that the moment demand and the shear in column C should increase still further. All right, so we do another analysis where we say, right, we'll now increase the amount of flexural reinforcement there more and reduce it in C more. And we get a further estimation. Let's look at what this means. The shortest piers are the stiffest. The shear is inversely proportional to the 1 over the height cubed. Therefore, the moment and approximately the reinforcement ratio are in proportion to the inverse of the height squared. Increasing the reinforcement ratio of the short piers relative to the long piers increases the relative stiffness of the short piers, so we attract higher shear to the elastic response. Allocating high shear to the short column increases its susceptibility to shear failure, of course. Displacement capacity of the short pier, we find, is decreased by increasing the reinforcement ratio. What we get by this procedure, if we follow it to its logical end, is we put all of the flexural reinforcement in that short pier, we have nominal reinforcement in the tall pier, and we end up with a very bad design. And it doesn't make any sense anyway to have a higher reinforcement ratio for the shorter columns than the longer columns. And though the young engineer who's done this and comes to the senior engineer says, okay, we need 4% reinforcement in that short pier and 0.5% in the long pier, the senior engineer says, no, we'll have the same reinforcement ratio in all of them to make sure that we get a rational design. So in fact, engineers are used to getting rid of the results of analysis when they don't seem to make rational sense to them. What about wall buildings? We see very much the same sort of system coming into play when we deal with walls, structural systems where we have walls of different lengths. We mentioned that the yield curvature is something or other which is inversely proportional to the section depth. In this case, it should be an L rather than H, and independent of the strength. So we could characterize the behavior of this wall and this wall by force displacement response. And the important thing to note is the yield curvature is going to be in inverse proportion to the length of the wall itself. And therefore, this wall here will have a small yield displacement, which is proportional to the yield curvature. This will have a larger one. And there is nothing you can do about that. There is no way you can get that shorter wall to yield at the same displacement as the longer wall. So force-based design allocates the base shear in proportion to the elastic stiffness, which is proportional to the length of the wall cubed, on the assumption that the short wall can be made to yield at the same displacement as the long wall. And this is impossible, as we've said. Strength is unnecessarily and unwisely concentrated in the long wall itself. We note again that since the long and short walls have different yield displacements and hence different displacement ductility demands, the relationship between force displacement or force reduction factor and displacement ductility demand of the structure is not obvious itself. As with the bridge case, we concentrate high shear demand in the element which is perhaps least capable of sustaining it. Something else I'll just very briefly mention is the business of converting between the elastic displacement that you estimate from the elastic response spectrum and the inelastic displacement response spectrum. And though there's getting to be more agreement nowadays, but there is still considerable difference of opinion. For example, here's the elastic displacement up here, and these are different estimates of what the different inelastic displacement might be for a structure with a force reduction factor of 4. If you use the equal displacement approximation, then you assume that the elastic displacement and the inelastic displacement are the same. Some countries use the equal energy approximation, which means that the inelastic displacement is very much larger than the elastic displacement. And in the United States, they have tended to use something or other which is very much smaller. The inelastic displacement is smaller than the value that they would get from the elastic relationship. Now this is very serious business if we accept that the most important aspect in terms of performance of a structure is the displacement, since this is related directly to damage by strains or by drift. We see that we cannot agree within a factor of 3 or 4 what level of inelastic displacement we might have, depending on which part in the world we are. Part of the reason for this is that displacement equivalence rules are based on inelastic time history analyses, and the representation of the initial response, the initial elastic response, has a very big influence on this, which has not been recognized. This is dealt with in the code, in the book, and I won't go on to it in great detail, but it's particularly the way in which the elastic damping is modeled in inelastic time history analyses. Normally, this is in an initial stiffness proportional damping is what it's called. We don't need to bother to go in it in great detail, but what it means is that if you make that assumption that the elastic damping is proportional to the initial stiffness and the structure goes into the inelastic range, you end up assuming much too much damping, much too much elastic damping in the system, and you underestimate the true displacement demand by quite a large amount. So the hundreds of thousands of nonlinear time history analyses that have been used in the past to justify relationships between elastic displacement and inelastic displacement are generally invalid because they have used a completely invalid elastic damping model. I might go into that a little bit in the final section, but it's gone through in great detail later on in the book. I mentioned earlier that this business of there is no obvious relationship between strength and damage potential, and yet our codes tell us that if we have an important structure, we should increase the strength to make it safer. Well, high strength does reduce damage in small or moderate earthquakes, so it has some value there. It does not necessarily reduce damage in the design or extreme earthquakes. It doesn't necessarily reduce displacements. It subjects the contents of the structure to higher acceleration. So if you're dealing with a hospital, designing it for higher strength, higher base shear strength may be a bad thing because you're going to have more damage to delicate instrumentation and so forth. And of course it increases the cost. Well, let's have a look at a very simple example of this. And again, we talk about a simple bridge column, and it's pretty much the same example as we had before, where we have a 2-meter diameter column and we vary the amount of flexural reinforcement in it. We know that by varying the amount of flexural reinforcement, we will vary the strength and other parameters as well. On the left-hand side of this figure, we have the assumption that we have that justifies increasing the strength. We say if the system has a particular stiffness and a particular elastic response, and we assume the equal displacement approximation, then by increasing the strength from S1 to S2, we increase the yield displacement. The maximum displacement is constant, therefore the ductility is reduced, therefore the structure is safer. Well, we've already said that there is an error in here because we don't increase the yield displacement. But let's look at it from the analysis when we really look at the response. And we do this by relation to a standard reinforcement ratio of 1.5%. As we change the reinforcement ratio, excuse me, we increase the strength if we increase it, and as we reduce the reinforcement ratio, we reduce it. Just have a sip of water, if I may. Thanks. Thanks, it's fine. So, changing the reinforcement ratio increases the strength as we expect. What does it do in terms of the displacement capacity? If we do sophisticated analysis to determine what happens to the displacement capacity, we see we see that the displacement capacity, as we increase the reinforcement ratio, is shown by this solid line there. It decreases. As we reduce the reinforcement ratio, we increase the ductility capacity. Well, that seems strange. Here we assumed that as we increased the strength, we would essentially increase the displacement capacity because the ductility remains constant. It's not true. Look at the ductility capacity. In fact, we make it even worse. The ductility capacity, reflected by the dashed line, reduces as we increase the reinforcement ratio. But of course, we also made a mistake in this estimate here in that we know that the stiffness will increase, and that's shown there by this dashed line over here. As we increase the reinforcement ratio, we increase the stiffness. The important thing is to compare the displacement capacity and the displacement demand. Now, if we actually take into account that as we increase the reinforcement ratio, we change the stiffness and therefore the period, we will reduce the displacement demand as we increase the strength. The final thing, though, when we compare the displacement capacity and the displacement demand is shown by this line here. The ratio, this is now estimating something which is relevant for the safety of the structure. As we change the reinforcement ratio from 0.5% to 4%, we change the ratio of ductility demand to ductility capacity by 7%. Almost nothing. It's within the accuracies of the calculation, certainly. So strength has almost no relevance to the value of the safety of the structure. And this Hardy Cross, once a great English engineer, back in the 1930s said, in structural design, strength is essential, but otherwise unimportant. It's a real conundrum, but it's an interesting sort of thing. And you can see in this case, strength is important, certainly, but it's essential, but it's not important. The actual value that you put into the strength has very little to do with the safety of the structure. And a design process that says to make the structure safer, double the strength is irrelevant. When we look at structures with dual load paths, what I mean here is this bridge that we've looked at in the past, perhaps, is now under transverse response, and it's pinned at the two abutments itself. Now, if that's the case, if it's pinned at the two abutments, there are two paths that carry the seismic forces back to the foundations. There's superstructure flexure, which is elastic. The superstructure will respond elastically because we don't allow inelastic response to that, whereas the piers we may allow to respond inelastically. The elastic path then is superstructure spanning between the abutments, which we've called here path 2, and the other one is the inelastic load path, which is column flexure, which is path 1 elastically and path 3 inelastically. So if we have a system where the piers go into the inelastic range and we try to model the behavior by the initial elastic stiffness, we see then elastically what we have is that the piers are stiffer than the superstructure. So we allocate more load to the piers than to the superstructure. But in terms of actual response, when we get to the maximum response and the superstructure remains elastic, whereas the piers reach their inelastic response, and we look at the effective stiffness now, we see that the superstructure is now twice as stiff as the piers, and we've allocated the strength incorrectly. How can we deal with that in force-based design? We can't. We have no idea of how we can do that if we base it on the initial elastic stiffness. So we've got a fourfold in this particular example change in the way in which the forces are distributed in the structure as a response of having an elastic load path and an inelastic load path. I'm going to skip through this because we'll come through it. Elastic modal analysis doesn't make any sense for reasons that I've already mentioned. But now just look at the typical hysteretic response of a structure in a simplified form. And think of what we do in force-based design. In force-based design, what we do is we say, well, what we're interested in is this point here. That's the maximum response of the structure. And that's what we're designing for. But what we use is an initial stiffness which is gone as soon as we go into the inelastic range. We never see that stiffness again. And some value of elastic damping, 5%, regardless of the structural system. So we use those two values to try and estimate what this value here is. Wouldn't it perhaps be more logical to use a stiffness value which pointed directly to this maximum displacement response, and also some level of damping which reflected the shape of this hysteretic response? Wouldn't it be more logical to use that to try and estimate this point here? And that's the essence of displacement-based design. Performance-based seismic design methods, and there are many of them, displacement-based design in the form that we're talking about is certainly the most developed, but there are other methods available. One form is force-based displacement checked. Sometimes this is called a displacement-focused force-based design, in which you check the displacements at the end of the design based on realistic estimates of the stiffness, which you do know at the end of the design process. But then that's a pass-fail system. You just check to make sure that the displacements are within the code level. Another one is where deformation calculation-based design, where you do the design based on initial stiffness, you put in the flexural strength, and then you put in the transverse reinforcement for the particular level of inelastic deformation that you get in a particular element. A rather complex system which we don't approve of. And then the third one is what we call deformation specification-based design, which is designed to achieve a specified displacement. And you can see the rationale here is that if we are designing for a particular limit state, which we can characterize by a particular level of damage, then we go from that level of damage to the causative strains or displacements or drifts. We can go from that to the displacement, and then we can say, if we achieve this displacement, we have just got to that particular limit state, the performance limit. And so a logical design approach, and clearly the most economical one, would be for a specified performance level to try and achieve in the design exactly that displacement. And that's the way in which we are doing this here. Typically, we use the secant stiffness to the final displacement, and hysteretic damping is represented by equivalent viscous damping. Direct displacement-based design, the approach that we're talking about, recognizes again that damage is strain dependent, as we've talked out, and we can therefore directly relate structural damage to displacement. We note that non-structural damage can be related to drift, and we therefore can relate non-structural damage to displacement itself. And then that leads us to the second time we've seen this slide here, which characterizes the procedure that we'll be looking at. The procedure is, first of all, to determine from the structural system, whatever it is, an equivalent single degree of freedom system which represents the inelastic, the fundamental inelastic mode of response, not the elastic mode, but the inelastic mode. Then we say that for this equivalent single degree of freedom system, we can characterize the response by a bilinear response of this sort of nature, where we can specify the yield displacement. And remember, we said that the yield curvatures or drifts are independent of strength, so we know this at the start of the design displacement, what the yield displacement is. We can characterize the design displacement by the performance limit state that we're concerned with here. So these are both known at the start of the design process. What we don't know, of course, is the strength. But what we're going to say is we're going to characterize the structure not by this initial stiffness, but by the secant stiffness to this known displacement but unknown strength. We then say that the third piece of information is results that compare the displacement ductility, which we know at the start of the design process, and the structural system and relate that to equivalent viscous damping. So if we know that we're talking with a concrete frame and we know what the ductility is, then we know what the equivalent viscous damping is. Then the fourth piece of information is the displacement spectra set, as shown here, where we can enter with the known design displacement, that's this value here, dependent on the displacement, the performance limit. We enter until we find the known level of equivalent viscous damping, and that then tells us what the period of the structure is. That's the effective period corresponding to this stiffness here. Let's look at that in a bit more detail of those first bits. We've said that in a structure, we can determine both the yield displacement and the performance limit displacement at the start of the design process without knowledge of the strength. Therefore, we know what the displacement ductility demand for that limit state is, and we can calculate what the equivalent viscous damping is based on the results of a large number of inelastic time history analyses. We enter the displacement spectra set with the design displacement, go across until we get the appropriate level of damping, this value here, and that gives us the effective period of that secant stiffness. Well, if we know what the period is, and it's a single degree of freedom system, we can invert the single degree of freedom equation. You know, T equals 2 pi square root of mass divided by stiffness. If we invert that, then we can say, well, we know what this effective period is, TE, we've just calculated that up there. We know what the mass of the system is, therefore we can calculate what the stiffness is. All right? If we know what that stiffness is now, and we know what the displacement is, then we know what the required strength is. It's a very simple process which has not required any knowledge of the initial stiffness of the analysis of the structure, which we don't know. So the procedure is to go from limit state to the displacement, from the displacement to the ductility, since we know what the yield displacement is. That gives us what the damping is. The damping and the displacement give us the period. The period tells us what the stiffness is, just by inverting the single degree of freedom approximation. And then the strength, required base shear strength at maximum design response, not at the yield, is given by the stiffness times the performance displacement. So it's an extremely simple process. And then the difficulties that come into it depend on different structural systems and so forth. How do we model them? In particular, how do we get from this structure here to this equivalent freedom, single degree of freedom system? And then how do we cope with the higher mode effects in terms of capacity design and so forth? In force-based design, displacements are considered, if at all, they're considered as a final process. And in direct displacement-based design, the structure is designed so that it achieves rather than is bounded by a given performance state represented by displacement limits. Force-based design uses an estimate of initial stiffness and elastic damping, typically 5%, to estimate the required strength and the final design inelastic displacements. And then the strength is distributed to members in proportion to the elastic stiffness. The process that we're using uses a calculated value for the secant stiffness, which is a correct value, equivalent viscous damping, and a damage-related limit state displacement to determine the required strength. And this strength is not distributed to members in proportion to elastic stiffness. We'll go into how we do that in later sessions. Let's just look at what this looks like in a very, very simple example here. And I'm not going to give all of the details in this particular case, but it shows some idea of what we're doing. We take an actual 5-story reinforced concrete frame, and we find that the effective height is about 2/3 of the building height. It gives us an effective height for this particular example of 9.25 meters. We design it for a drift, a maximum drift of 2%. We'll find that in frame structures, almost always the code limit to design drift, which is dependent on non-structural damage, will govern. So normally that's what we will do. We will design for the design drift. All right, with that, with the knowledge of the effective height and the drift limit, we calculate that the design displacement is 185 millimeters. We calculate because we can calculate the yield displacement as I've mentioned earlier, we calculate that the design displacement then is 3.25. We calculate the mass from equations we'll give later. Approximately 80% of the total building mass is shown as 4,500 kilograms, or kilonewtons divided by G. We calculate from expressions which we have what the equivalent viscous damping is. Here's the example shown here. Here's the design ductility. Here's the level of damping shown here, 17.5. We go in with the design displacement to the 17.5 curve. That tells us that the period is 2.5 seconds. With that, then, we go to calculate what the effective stiffness is, just putting in the particular values here. And that gives us a stiffness of 2,900 kilonewtons per meter. And the base shear then is simply calculated as 536 kilonewtons. And it's all the calculations that's involved really for this, apart from the initial ones where we needed to calculate what the effective height was and what the yield displacements are. But it's a very simple process and I think intellectually fairly satisfying because you're not making the sort of approximations you would have to do otherwise. I'll move through this very quickly. Structural limit states, we've mentioned that we could be designing for serviceability limit states, damage control limit states, and survival limit states, and we provide information on the appropriate strains and drifts for these cases. Generally, we design only for one limit state, typically the damage control one, or perhaps damage control and serviceability. If more than one limit state requires detailed consideration, then the required strength is calculated for each limit state and the highest strength of the two is adopted. Right. That's the end of session one. I'm not sure what we're doing. We started about 40 minutes late. So if you have any questions, we hope to leave time at the end of each session for maybe 10 or 15 minutes of questions. So if you have any questions now, feel free to ask them. Alternately, what we'll do is just go and have a coffee. So are there any questions at this stage? Probably it'll have more questions when we get into the detailed sections of the presentation. But I hope you will ask questions because there will be areas that you find to be difficult to accept, and you should ask questions so that we can clarify these for you. Okay, thank you.